Good evening everyone, am I audible? Okay, sure, let's start. So a very good evening everyone. I welcome all of you to this session where we are going to talk about our next topic. Yesterday we have already completed with the binary search tree, and today we are going to explore fundamental basic idea about binary heaps, which I believe that this concept are the basic where questions will be asked in the examination. Okay, so do not ignore that. Okay, fine, it's a very fundamental, it's just a properties. No, they basically target this thing for creating question in GATE examination. Okay, so let's begin here. What we have completed yesterday, so we have seen binary search tree, BST construction, comparisons, number of comparisons we have seen, and also we have seen the insertion sequence, a question related with insertion sequence. So these all things we have already seen. Now what we'll do today here, okay, so as I promised that I will tell you, I'll talk about the traversal today. Okay, so keeping my promise, we will talk about traversal, binary traversal, BST traversal. We'll talk about that. We'll talk about here today CBT, complete binary tree, and its property. This is how the heap start, and we will also learn about max heap and min heap. Only we can cover the definition part, max heap or min heap with CBT property. Okay, so this three thing I am targeting. Let's see how much we can cover from this. Okay, okay, this possible in order traversal. Okay, now this is not the thing that I want to start with, so let's start with traversal. Okay, now I'll explain you three traversal technique where we can do the traversal. We can find the traversal in very simple possible manner. Okay, simplest one. Okay, simplest one. Now when we talk about traversal, it's a process of visiting nodes of the tree. Okay, that is sure that we are visiting nodes of the tree, and that process is called traversal. Okay, so traversal, there are three categories of the traversals are there, that goes into the depth, and one category of the traversal goes into the breadth. Okay, so one category is breadth, another category is depth. The three traversal in order, pre-order and post-order are basically the traversal which is go into the depth first traversal. Okay, and the level order traversal, level by level. Okay, that is basically a breadth first traversal. Okay, so two categories are there. It is more or less related with the graph traversal as well. Now these three traversals are we will talk about in order. We'll talk about depth one, and the depth one is consist of in order, pre-order and post-order. The depth consists of three traversal. Okay, now how we traverse this, and that sequence is we will go to the left, then we come to the root, and then we go to the right. This is the order. Okay, and I can teach you within 5 seconds how to get, because in examination it is not about it's not a theoretical examination, so we have to really very quick in identifying the traversal, what the traversal is. So this is the sequence that it follows. Pre-order is root, left and right, root, left and right, and post order is left, right and root, left, right and root. Okay, this. Now the idea here that we are going to go to the left first, but if it is a node we print, if it is not a node then we recursively call on the left and right subtree. If it is a node then print. Okay, so idea is that if we go to the left, okay, if tree if we go to left or right, if single node we visit the node, otherwise we recursively visit in given order. Okay. Now there are three statements are there. When you look at the actual traversal, there are three statements are there. Left subtree, then root, then right. Root, then left subtree, then right subtree. Left subtree, right subtree and root. So now if this is a node, okay, and if I talk about in order traversal, I will write this three statement here. Okay, so this statement is left, then the statement is root, and this statement is right. Look at the trick here to understand how the traversal work. I'll write three edges here. It is not for your semester examination. This is for wherever you have to find the answer very quickly. So three edges I will draw and identify that for in order, middle one is the visiting of the node. Middle one is the statement where we visit the node, middle one. Okay. So root is in the middle. Now once you get a tree and somebody asks you that find out the in order traversal, in order, then what you will do, among the three edges, the middle one is the visiting the root. Okay. So you draw all the, for all node you draw the middle edge. Okay. For all the node you draw the middle edge. Why sir middle? Because in order traversal, middle one is the visiting of the root. So in this traversal I have put the edges in the all the middle part. Left and right doesn't matter in this case. Now after doing this, we perform tracing. What is the tracing? Tracing is an outer line. Okay, we draw an outer line into this outer line, just like a kid, or when we are small, we used to draw tracing in every possible figure or image. Okay, so similar tracing we will draw, and whenever this tracing touches the middle line, we perform print. Result in order traversal. So whenever your tracing touching the middle line, you do the print, it will result in order traversal. Okay, as simple as that. How? Look at here. I am drawing a tracing and my tracing touches the middle line. I have already have middle line for every node. Do the print, it will give you the in order traversal. Look at here. Now this is tracing 12. Okay, so right here 12. Okay, tracing 18, 24. 26, 27, 28. 26, 27, 28. Tracing 56. 56. Tracing is coming 190, 200. 190, 200. 213 over. 213 over. This is something related with recursion tree. Okay, this is something related with recursion tree. Now for your better understanding, let me say one more time that whenever tracing touching this middle line, you perform the print operation, it will result in order traversal. Okay, look at here, come here in this case, this 12, 18, 24, 12, 18, 24, 26, 27, 28, 26, 27, 28, 56, 190, 200, 56, 190, 200, and in this is done. Okay, so this is how you can, without any other method, without any other trouble, you can find out the in order sequence of BST. Now observe that this sequence, this is a property of this sequence, that in order traversal of a BST results in order traversal, not every tree of BST is increasing order sequence. This is the property. Many times it is explored in the examination, increasing order sequence. Okay, increasing order sequence. Huh? So that's how you can find out the traversal, and you can say that it's a increasing order sequence. Now coming to the pre-order. Okay, 3 lines again for a node. Okay, 3 lines for a node. Let me write here, and here this line, and this line. The first one is the root. Okay, the first line is for root. This is for the left, and this is for the right. Root, left and right. So now it says that this line, this tree, if I want a pre-order traversal of it, okay, I need to focus on which line? The line this here. Root, left and right. Root, left and right, root, left and right, root, left and right. This one. Root, left and right, root, left and right, root, left and right. This and this. Okay. And now you can say that if I draw tracing and it is touching this line, it will result in pre-order traversal. Okay, so let's draw the line, and immediately it will touch 56, 26, 18, 12. Okay, so 56, 26, 18 and 12. Okay, now come here, no touching. 24, I'll go this side, then I'll come back. 28, 27, so 24, 28, 27, I'll go this side. 200, 190, 200, 190, 213, then done. 213 and then done. Okay, so this is your pre-order traversal, root, left and right. Observe that this element is a root of the tree. First element is the root of the tree. Property of what? Pre-order traversal. Okay, property of pre-order traversal. Okay, first element is the root, and most importantly, when you have a pre-order traversal, I can identify left subtree and right subtree also. How? I can identify left subtree and right subtree also. We know from the BST property that the element on the left will be lesser than 56 and element on the right side will be greater than 56. If I observe each element into this, I can identify which element on the left, which element on the right based on the property of binary search tree. So now if I have to put a, let's say, bracket or let's say box, lesser, 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 up to here it is lesser, 200 is greater. So these elements in the pre-order traversal is on the left subtree, greater, greater, greater. These element will be in the right subtree. This is in the right subtree. Okay, so I can identify from the pre-order traversal, root I can identify, left subtree I can identify based on the property of a BST, and right subtree I can identify from this traversal. Okay. Last traversal is what? Last traversal is post-order traversal. Last traversal is post-order traversal, and post-order traversal says left, right and root. Where is my root? Root. Now you are going to answer me this question, that what is the post-order traversal of this? This is the root part. This is the root part. This is the root part. Root, root. Please give the sequence of post-order traversal. Give the sequence for post-order traversal. Okay, give the sequence for post-order traversal. I think you can do it. Please answer that what will be the post-order traversal for this binary search tree. Go ahead. Come on. You can answer very easily. Very good evening, Nishu. Great, good response. Sir, I am Pathikrit Hajra. Yes, beta, I remember you, Pathikrit. Jadavpur University, IT. Thanks you for your guide. Well done, very well done. Okay, just only one thing. There is no gap in terms of placement in for IT and computer science. Huh? Do remember this thing. Sit for every possible company. Adobe, HP, Microsoft, Google, probably Intel, every company visit there. Okay, so my advice to you, you will not have too much academic pressure in Jadavpur IT branch. Okay, IT branch you will not have that much academic pressure. Start preparing from the placement from very much from the beginning. Every big company is going to visit there. Whatever company comes to visit IIT Kharagpur, NIT Durgapur, they surely visit Jadavpur. Okay, every big company, you name it, every big company is going to visit there. So my advice to you that from the day one you target the company, that which company you want to work and start preparing. Okay, start preparing, and definitely you'll get a very good opportunity in terms of placement. Great. So now let's start the tracing here. Let's do the tracing here. So first is 12, 24 and 18. So 12, 24 and 18. Okay. 27, 28, 26. 28, 27, 26. 190, 213. 213, 256. 256. Yes. Of course, yes. It is. They ask you very specific question. You have to skill. When you are preparing for the big companies, when you are preparing for the big companies, then your coding skill will come into the picture. They will test you based on the coding skill. First thing, if you are computer science graduate, you will be tested based on your coding. So you have to problem solving skill to be developed. Okay, algorithm design. I am talking about big companies. I am not talking about small company where your, I think, gate preparation will be enough for service based company. But now they see TCS NQT that started. They also started testing your problem solving skill. TCS NQT, I think you might be aware of. But your problem solving skill will be tested. Okay, so coding, understanding, lead code, this sort of thing you have to practice. Okay, and you have to develop new situation. System design also they test, like meta test system design also. Okay, is it correct? 12, 24, 18 and then 20, this is wrong. 27, 28. So 27, 28. Then 26, then 190, 213 and 256. Property that the last element is the root element. Okay, root is the last element. Root is the last element. Lesser than root. So now this whole bunch, 12, 24 lesser, 18 lesser, 27 lesser, 28 lesser, 26 lesser. That's all lesser. So this is in the left subtree. And remaining will be definitely in the right subtree. Remaining will be in the right subtree. Okay. Okay. So that I changed that. Now, so this is your traversal, and using this technique, this slide, you can figure it out any traversal of any tree, but binary. We talked about binary tree. Okay, binary tree. Great. Now let's come to the our part that I said that we are going to cover. Is first thing is the CBT, complete binary tree, one of the very important structure. And if you look at the question, more and more things you will find that it's a CBT. Okay, so what is a CBT? Let's have the definition first. Now, definition of the CBT is a binary tree. A given binary tree is a CBT. CBT. Okay. If all levels are full, except last. Okay, last level may or may not be full. Last level may or may not be full. Okay. Second, in the last level, second point, in the last level, element will be arranged strictly left to right. It is not enough strictly left to right. This definition is there. This. Okay. So every level full except possibly the last level, or in the last level, element will be arranged strictly left to right. Okay, that is a full binary tree. Let us see this structure. Okay, let us see this structure whether it is a CBT or not. Here every level is full, 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 full. Every level is full. Then if I ask you this very simple question, whether this is a CBT, complete binary tree, okay, answer is yes. Is it a CBT, CBT structure? Answer is yes. Sir, what about the last level? The last level may or may not be full. Okay, it may be full, it may not be full here. So this is a CBT structure. What about this structure? Is it a CBT? Okay, is it a CBT? CBT structure? So now again, let's say definition says previous last all level full except last. So yes, all level full 1, 2, 4. Last level may or may not be full. So yes, it is not full. Okay, so yes, this also CBT. Answer is also yes, that this structure is also a CBT. Okay, this structure, given structure is also CBT. Why it is a CBT? Because previous to last level full and last level is not full, that is okay. Okay, that is okay. Now what about this structure? What about this structure? Is it a CBT structure? So let's see the definition. All levels should be full except possibly the last. But here problem is there. In this CBT, the last level is not full, fine, but before that, this level is also not full. Okay, it's not CBT. Huh? Not CBT. Why? All levels before last level is not full. Before last level is not full. Okay, it is not full. Correct? It is not CBT. Okay, it's not CBT. What about this structure? Is it a CBT? So all level before the last level full, full, full. What about this structure? Is it a CBT? So again, answer here in this case is what? Answer is no. It's not CBT. Okay, it's not CBT. Why? Because the definition says in last level, node element must be node must be strictly left to right. Node must be strictly left to right. Okay, strictly left to right. Now here, what is the problem? That this is having a right child. This node is having a right child. Okay, right child, but no left child. But no left child. Okay, it is having a right child, but it is not having left, and it has what it says, it's strictly left to right. So this is having missing a left child and having a right child. This is not allowed in CBT. Okay, you have to arrange, if you are having 3 nodes, you cannot miss one and give this one or this one or this one. Who is the which one should be filled first? So its left node must be filled first, then right, then this left, then this right, then this left, then this right, and then you go further. Okay. Now this is okay. This is a CBT. Okay. This structure is a CBT. This is a CBT structure. Okay. This is a CBT. Full left, right, left, right, left, 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 right, left, right, left. So left or right maybe, but yes, 5 is there. So left. This is a CBT structure. So the first point is that why we are discussing CBT at all. So very much important thing is your heap are the first statement. Heap, binary heap is a CBT. Okay, binary heap is a CBT structure. Binary heap when we talk about is complete binary tree. Okay, first thing is that it is a CBT structure. So it has to, we will fill the values, but it is a CBT structure. Now here in this case is that if you have a CBT, then this is a property. Okay, and we have a property of CBT comprised of two things. Okay, how many nodes CBT can have? CBT can have of height h. So we are talking about this thing, that how many nodes a CBT of height h can have. So how many nodes? How many? Let's say maximum number of nodes. Maximum number of nodes of height h CBT. Okay, CBT. Now understand here, height is h, here it is 3. Okay, and if I say that total number of node, okay, total number of node is n, how I will calculate total number of node? So in the root we are having one node which is 2 to the power 0. If I go to the height 1, I have a node height 1 2 to the power of 1. If I go further to the height number 2, then I have a 2 to the power 2 node. And if I go to the height h, I will have 2 to the power h nodes. Okay. So maximum number of node when it will occur? When every level is full. 0, whatever, every level, complete, last level is also full, packed, no space, house full. 2 to the power 0, first 0th height, 2 to the power 1, first height, then second height, then third height. Okay, 2 to the power of h. This is a geometric progression, GP series, and the sum of the GP series is a ratio to the power n minus 1 divided by r minus 1. A is first term, n is number of terms, and r is for the ratio between two consecutive digit sequence. Here what is a? So a is equal to 1. What is n? Number of terms. So 0 to h, don't forget 0 to h, hence h plus 1. And what is r? The ratio between 2 to the power 1 and 1 is 2. You put the value 1, 2 to the power of h plus 1 minus 1 and divided by 2 to the power 2 minus 1. So that is equal to 2 to the power of h plus 1 minus 1. This is the maximum number of node. Welcome. This is the maximum number of node your tree can have. Okay, maximum number of node this tree can have, maximum. Beyond that, it is, I have packed it, packed everything. Okay, I am giving you a homework. If n is equal to, n is total number of node. If n is total number, capital N. If n is total number of node, then you will simplify what is the value of h. If n is the total number of node, find h. Find h. Okay, find h in this case. This is the maximum number of node possible. Now the question is, what is the minimum number of node? Okay, so in minimum number of node, the idea here in this case is that height is still 3. Height is still 3 and previous level is full. If height is still 3 and the previous level is full, then what is the minimum number of node we can have? So for that, what we can do is that previous level I cannot help anything, I cannot do anything with the previous level, but definitely in the last level I can have only one single node. Okay, I can have only one minimum. Then that is, if height is still 3, if I cut this also, if I take out this also, then height will not be 3, height will become 2. Okay, so I can have at least one node, only one node is possible. So that is the minimum number of node in this tree. This is maximum and this is minimum number of node in height, of course, height h. In with height h. With height h. Correct? Now, if it is height h, then fine, no issue. Height h, then now let's calculate. So what will be the total number of nodes? So it will continue like same like previous, 2 to the power 0, 2 to the power 1, and this time it will up to only h minus 1, because only up to h minus 1 is full. Previously it was h, because h is also full, but now here it is full only up to h minus 1, and in the next level how many nodes we are having? 1. So plus 1. So now my geometric progression has changed. A1 number of terms is, in this case, is 0 to h minus 1. So h and ratio is same. One term lesser, 2. So what it will be? 1, 2 to the power of h minus 1 divided by 2 minus 1 and plus 1. So it will become 2 to the power h minus 1 plus 1, 2 to the power of h. So CBT, another property of the CBT, two more property, then I will explain you the definition. CBT is having number of node as 2 to the power of h minimum, and maximum 2 to the power of h plus 1 minus 1. This is the about property of a CBT. Heap also you can say the same thing. Okay, heap also you can have the same thing. Great. Now, any CBT, okay, this is another property of the CBT, complete binary tree. Achha, are we clear up to this? Are we clear up to this? Is it okay, everyone? Great. Good. Okay. Now, if, thank you. If number of node is n, okay, in CBT, if total number of node is equal to n, total number of node is n, then the number of leaf is equal to ceiling value of n divided by 2. Again, one more fundamental, this. Okay, you can take this example that there are 10 nodes are there. Okay, ceiling value, I think you will be confused. 10 nodes are there. Okay, 10 nodes are there. Then number of leaf will be 10 divided by 2, and that is equal to 5. Now suppose if I if I take out this, suppose if I take this out, it is gone. And if I say number of leaves in this case is here, because that is perfect na, 10 by 2 5, so no issue. But if I say this, then number of node is 9. So number of node here in this case is 9. So 9 divided by 2, ceiling value of 4.5, and that is equal to 5. 5 leaves are there without any doubt. Count. 1 leaf, yesterday I told you what is a leaf. No children. So 1 leaf, 2 leaf, 3 leaf, 4 leaf and 5 leaf. Okay. So this is another property of the CBT before I go to the definition of heap, that it is having number of leaf as capital N by 2. Number of internal node which is not leaf, is equal to floor value of N by 2. Floor value of N by 2. Okay. So here again it is having 11 nodes. So if N, total number of node is 11, then it is becoming floor value of 11 divided by 2, and that is equal to floor value of 5.5, and that is equal to 5. So there are 5 internal nodes are there with no children, 1, 2, 3, 4 and 5. As simple as that. If you say, sir, what is the number of leaf? The number of leaf will be 6. Ceiling value of 11 by 2, that is equal to 6. Okay. You will not believe that this is a GATE question, that a max heap is having 169 nodes. It's a GATE question, you won't believe this. 169 nodes. Number of leaf tree is having. It's a GATE question. How many leaves? A max heap is having 169 nodes. Number of leaf the tree is having. How many? This is a GATE question. Which year? I think it is in 21 or 22. That I need to search, but I think in 22 or 23 they have asked, as if I remember. Okay. So number of leaves will be what? Number of leaves will be, how many leaves? Ceiling value of 169 divided by 2. Okay. And that is equal to 84.5, and that is equal to 85. So answer is very simple, 85. Okay. 85 is the answer for this question. Great. So now you have learned all the properties of CBT. we are ready to introduce the min heap and max heap. Okay, we are ready to introduce the min heap and max heap. First of all, very clear that these are not BST. Okay, heap is not a BST. So what is the definition? A min heap, okay, a min heap is a CBT. First thing, it's a complete binary tree in which for each node the key value at parent, okay, the key value at parent node is lesser than the key value at its children. Now, why we need this? What is the application of this? Let me also tell you this, that the key value of the parent node is lesser than the key value at its children. So 6 is lesser than 7 and 12, 7 is lesser than 10 and 15, and 12 is lesser than 17. It's a CBT. Okay. Now we are having a algorithm design technique. Yeah, we have the requirement in some design technique in which we want among the given choices, like I'm telling you that suppose you are shopping in a app, online shopping you're doing. Now the same thing is present in various apps, different apps on different prices. Same thing you are getting in, like one is 100, another is saying 80, then 70. Which one you will pick? Okay, so obviously that you are going to pick the one which is having minimum one. Now this is a huge application in designing of algorithm, and that algorithm design technique is called a greedy method, where we want to minimize the overall cost, or sometime we want to maximize the overall cost, overall, let's say, function. Okay, we want a maximum value, like profit you want maximum, cost you want minimum. So in greedy method we use this data structure. Okay, in greedy method we use heap data structure, and every time we have to select something in a group, I need to select the minimum, we select the root element. Okay, we select the root element, then we do some magic chumantar, and again the minimum goes up. Okay, the minimum goes up. So what is a min heap? The first part is the root is the minimum element. Okay, root is minimum element. My question to you is, where will be the maximum element? Root is the minimum element. My question to you is, where maximum element will be present? Where maximum element will be present? Where maximum element will be present? Where it will be present? Very good. So it will be present is as one of the leaf node. Maximum will be present in me is one of the leaf node. One of the leaf node. But where we don't know. One of the leaf node. Okay. It will be one of the leaf node will be maximum. Will be maximum. Okay. One of the leaf node will be maximum. Can be any leaf. Very good. It can be any leaf. Very nice. Now, similar goes with the max heap, that the key value at parent node, the key value parent node is greater than key value at its children. Okay. One more point, that we store this max heap in an array. Okay, we store max heap in the array. So how this will be stored in the array? It will be stored in this manner: 17, 15, 10, 6. Okay, 10 is getting repeated here. Okay, fine. Let's make it 12. Okay, let's make it 12. 10, 6, 12 and 7. Okay, this is how it will be stored. So how we are maintain the heaps CBT and how it is being stored. Okay, so it is stored in array. It is stored in linear data structure. Stored in linear data structure, which is called as array. Let me ask you very simple question based on this. Let me ask you very simple question based on this. Among 1, 2, 3, 4, these options, which one represent binary max heap? Okay, binary max heap. Go ahead, answer. Very nice. Good. Very good. You identified that it is C. Let's see. Let us see. Acha, only one person has identified. Okay. Rest complete. All. Okay. Let me put into the two part so that you'll be able to understand. Okay. Let's see 25, 12, 16, 13. It is okay. But now see 10. Option A. Max heap. 10. How it is possible? 10. 10 is not possible. Achha, 10 is possible. 13 is not possible. Sorry. 13 is not possible. How 13 can be child of 12? No. Why, sir? It's a max heap. Okay. It's a max heap. It is not possible. 25. 14. Fine. Max heap. 13. Max heap. 16. How 14 can have 16 as the children? If it is what? It's a max heap. How is it possible? Not possible. C. Option C. 25. 12. Okay. 14. 16. Good. 16. Then 13. Fine. Lesser. 10. Lesser. 10 lesser, 8 lesser, 12 lesser. C is correct. C is correct. C is the right answer over here. Okay. C is a right answer. So C is the correct. At least this one you can check. Last thing, then we'll wrap up the session for today. Okay. Last but not the least, the last but not the least is this. If I want to insert a new element in any binary search tree, understand the process. If I am inserting new element, so now up to here it is fixed. The next position for the CBT, if I insert the value, let's say in this 30, okay. So first of all, I should insert into the position so that the CBT property is not violated. Okay, the CBT property is not violated. To insert 30, where to insert? So I'll insert here 30. Now last position, 7, 8th position. Then we will start comparing with the parent one. Okay, and it now the game of the throne will begin, and we'll compare with the parent, and if the parent key value is lesser and it is a greater, because we are working in a max heap, we'll drag it down. Okay, now what will begin here? The game of who will become the king. Okay, so in this case, the first thing is we notice that 30 is greater, 13 is lesser. It will say, Papa, come down, I will go up. So it will go 30 and this will become 13. Again, now it will not spare only the parent, it will go to grandparent as well. It will say 14, 30, I am greater, you come down this position 14 and I will go up in your position, that is 30. It will not even spare the great grandfather. It will say 25, okay, you come down, I will go up, and it will sit on the top. Capability. Okay, so now this is 30, then this is 25, then this is 14, and then this is 13. You don't need to do anything other than, okay, other than here you have to only compare with the parent, and if it is smaller, drag it down. This is the swap that we performed. Okay, when I inserted the 30, 30 compare with 13, 13 comes down, 30 compare with 14, 14 come down, 30 compare with 25, 25 come down, and it reaches to the top. Okay, it is reaches to the top. So this reaches here. Okay, now my homework to you, tomorrow you will try to complete, insert the value 42, 9 and then 52. Insert 3 element into this. Okay, this is your homework, that in this case tree, in the tree you insert the 3 key values, okay, one by one at the end, 42, 9 and 52. Okay, that is all for today's session. CBT is very important, and I already said you have a quotient from basic property, and that defines the heap in this case. Insertion also I said how to insert an element, that also I explained you. So max heap, min heap, CBT, traversal and insertion. Many things we have covered in, let's say, less than 1 hour. Thank you all of you. I will see you tomorrow. Fine. Goodbye everyone. You are doing homework question. Huh? Bye. You can see it.